So good morning. This is John Shepard. I'm the Chief Science Officer at the University of Hawaii Cancer Center in Kaka'ako, Hawaii. And this is the Artificial Intelligence and Precision Health Institute Affinity Talk. I'll introduce my speaker here in a moment, but I just have a few slides that I would like to share with everyone. So welcome. Here we hear from leaders in the field to discuss AI and healthcare trends. We want to bring together researchers from a variety of fields, including clinicians, computer scientists, advocates, all with an interest of how AI can better be used in healthcare. So we want to foster collaboration, interactions, and solve problems in cancer that were thought to be unsolvable a decade ago before the broad use of AI. The talks are roughly 30 to 40 minutes long, and we'll have an interactive QA and discussion section at the end. If you want to provide feedback, please do at my email address. This is co-hosted by several different entities here in Hawaii, such as the Hawaii Data Science Institute that trains students in the use of machine learning. Also, the University of Hawaii Cancer Center here in Kaka'ako, the only NCI-designated cancer center in the Pacific, and also the Artificial Intelligence Precision Health Institute, which we have as a vehicle to train students and faculty in the use of AI in research. We have a generous compensation to all of our speakers. That's why we get such great speakers every month, and that consist of a Stein with the AFI logo on the front of it. This week, we have Dr. Rajesh Bhayana. He's an abdominal radiologist at the University of Medical Imaging in Toronto. He's a technology lead for his Department of Medical Imaging and an assistant professor in radiology. He completed his residency at the University of Toronto and was chief resident, but also did his fellowship. I presume that's fellowship in oncology, right? In abdominal imaging at Mass General. He has a focus of bringing practical applications of AI, specifically or particularly large language models in radiology to improve patient care. We have a paper of the week. I don't see where it didn't come up, did it? I'm sorry, guys. There's a paper of the week which he'll be talking about this morning, and it was in radiology. And I think last month or 2 months ago, we came across it from Aunt Minnie. So it got some play, got a lot of press, and we thought we would have you give us a talk on those topics. So thank you for joining us, Dr. Bhayana, and I'll turn over to you.
Thank you, John. I'm just going to share my screen. Can you see that okay?
Perfect.
Perfect. Okay, so thanks so much, John, for the kind introduction, and thanks for having me today. It's bittersweet. Sweet to be here, but also bitter to see these backgrounds of trees and warmth. I'm in Toronto, Ontario, Canada, and it's raining and below zero and slush on the ground everywhere. So it's not so pleasant on where I'm at right now. But again, thank you for the introduction and having me. So today, I'm going to be talking more generally first about large language models or LLMs and how we can leverage them for clinical impact today. So I am first and foremost, as mentioned by John, a clinical radiologist. And so that's the focus of my research. So rather than looking at theoretical future applications of AI, I focus on how we can use LLMs to solve real world clinical problems now and how we can implement them at our institution and other institutions in real life practice. So with that in mind, I want to start with 3 main points that are all related. Okay, and so number 1 is that the intelligent optimization of already existing foundation models already enables many clinical applications that can improve patient care. And that's because, in my opinion and in practice, there are many clinical problems and inefficiencies that we see on a day-to-day basis when we practice. And those inefficiencies that we see often intersect with what is currently possible with AI. And that's where we're going to spend the bulk of the talk today, looking at examples of what we are doing in radiology across the clinical pathway, with a special attention to the article that John introduced of ours that was published in Radiology. Number two, a side point, a lot of AI research in the world, in my opinion, today happens in silos. So you have the smartest technical minds who work on technical problems like building domain-specific foundation models, but without the clinical expertise to understand the actual real-life clinical issues that we see on a day-to-day basis and that they might solve. And so many of the technical papers have obvious clinical errors in them, and the inverse is true too. So the main point here is that we must more aggressively collaborate to make more impact. So it's great kind of what you guys are doing, and we have our own AI hub, for instance, that also tries to do the same. Number three, in medicine, we focus a lot on AI safety, bias, privacy, other risks. These are very important and must be considered, but we should not use them as an excuse to sit on our hands. So for applications that are validated, offer concrete clinical advantages, we need to get them into practice in supervised and safe settings, in my opinion, sooner rather than later. Again, if we know something augments what we do, improves care, improves efficiency, we should facilitate expedited deployment in safe settings. The main point is going to be point one, but the other two obviously closely related. So I'll start with a brief intro to LLMs, limitations, i.e. why we cannot just throw these models into the deep end and expect them to work as expected out of box. And then in the second half, or after talking about how we can optimize them for specific tasks, and talking about how you can do that for various applications, in the second half, we'll explore some of those applications, focusing on what we are doing in radiology in Toronto. And then we'll wrap it up. So first, a bit of background, just so that we're all on the same page and can kind of frame how we think of LLMs in the same way. So I think most people have interacted with LLMs through chatbots. And chatbots just refer, key point, to end user applications that mimic human conversation. So they're not new. The first dates back to the 1960s. It was called ELIZA, gave you pre-programmed responses to your queries. The original Siri and Google Assistant from the 2010s, also chatbots, came a long way, but still very limited. So no, we're not here to talk about these. We're here to talk about the most recent wave of chatbots like ChatGPT, and more specifically, the LLMs that underlie them. Again, these chatbots like ChatGPT are just applications that are built using large language models. So for ChatGPT, you can select one of many different models today. For instance, GPT-4o, or now even GPT-4.5, I should say, or reasoning models like O1 or O3 Mini. For Google's Gemini chatbot, there are also several models you can choose, including Gemini 2.0 Flash Thinking most recently. And there are other companies that are making very high quality proprietary models like XAI, Grok 3, Anthropic with their Claude family of models, and they're very good at coding. And in addition to these state-of-the-art proprietary models, there are many open source models, most famously Meta's Llama 3 and Llama series of models. Also, DeepSeek made a splash recently, no pun intended. And similarly, you have the DeepSeek application, which is a chatbot application, which is owned by a Chinese company, and then the LLMs that they are built on. In this case, are open weight models that you can actually download and host anywhere, as long as you have enough compute. So even at our various hospital institutions, through secure cloud, we can host these models in a secure way and use them if accessed appropriately. Namely, DeepSeek v3 is analogous to the 4o from OpenAI, and their reasoning model DeepSeek R1 analogous to OpenAI's O1 reasoning models. So a lot of letters and numbers in these names, which can be very confusing at first if you're not familiar. But for now, the most important thing to do is to distinguish these commercial chatbots like ChatGPT, in which the inputs and outputs are owned by the respective companies like OpenAI or Google. These should never, ever be used clinically or with sensitive information. And in contrast, the LLMs themselves, like GPT-4o, which are just giant neural networks that you can use in a secure way in your own applications in healthcare if you access them appropriately. So how do these LLMs work? So this is largely beyond the scope here, but I highly recommend this deep dive um, uh, on LLMs by Andre Karpathy, who's a thought leader in LLMs, and this video is on YouTube. But essentially, these LLMs are just large neural networks that are trained on a lot of text, almost the entire internet. And these neural networks are pre-trained to predict the next word or token in a sequence. So given a certain input or context, it tries to predict what's next in that sequence based on patterns and associations that it's learned from the pre-training data. And there's knowledge in that. So for instance, if the context is the most common cause of pancreatitis is, it might predict gallstones as the most likely next word, or alcohol as the second most likely next word. For pre-training, it's helpful to think of it as essentially compressing the knowledge of all of the internet data into the model's parameters, kind of like a zip file. But it's a lossy compression. So we can think of the knowledge of an LLM like a gestalt of the entire internet or a vague memory of the entire internet. And it's important as a mental model as to how we think of these models. This image is from one of Karpathy's talks. So pre-training produces something called a base model. And then post-training involves fine-tuning that model so that those next word predictions that we talked about are more useful for us, like acting as a helpful assistant or writing our emails or answering our questions, often called the instruct version of the model. And that's what we're basically interacting with ChatGPT. But why have these models become so good so recently? So briefly, the three biggest factors that enable this acceleration are one, the transformer model. The T is in GPT is transformer, introduced in 2017 in a paper called Attention is All You Need from researchers at Google and DeepMind. Transformers enable better understanding the context of sequential data or in sequential data and processing data in parallel, which enables efficient unsupervised learning. The availability of massive amounts of unlabeled internet data for pre-training. The P in GPT stands for pre-trained. And then the availability of massive amounts of compute, specifically massive clusters of GPUs needed for both training and inference, i.e. what helped make NVIDIA the single biggest company in the world. So LLMs increased in size referring to the number of parameters. I'm sure many of you have come across or are familiar with scaling laws. The idea being that as you scale up model size, i.e. parameters, training data, dataset size, and compute, the model performance will typically increase or continue to increase over time, shown here as a decrease in loss as you scale up all three in tandem. This is from the 2020 scaling laws paper from OpenAI. It's an ongoing debate as to whether these performance improvements are going to continue as we scale, acknowledging that we only have so much data on the internet. But as the models got bigger, the key takeaway is that they became more flexible. Okay, so that's the takeaway of this slide. In this chart, we have performance on a task on the y-axis and number of examples of that particular task provided to the model on the x-axis. So smaller models like the one in green here need a lot of examples, labeled examples, to improve performance. Whereas bigger models like the one in blue, this happens to be GPT-3, perform very well with few examples or even zero examples on language tasks, i.e., they can be easily adapted to multiple different tasks without needing a lot of additional training examples or any additional training examples. And this flexibility to perform well on language tasks out of box was widely showcased in late 2022 when ChatGPT was released. So we found uses for it immediately that showcased its flexibility, like writing emails, code. Somebody famously coded the entire game Flappy Bird early on by just following its instructions. And now the newest models are very proficient coders. The models demonstrated human-level performance on several professional and academic benchmarks, like comfortably passing the bar exam, for instance. So ultimately, language is the code of thought. It's how we think, including in healthcare. So of course, this is very powerful. In medicine on USMLE questions, the models have improved significantly over a short period of time, with recent models performing very well on general medical questions. In radiology, we published some of the first benchmarks in any medical subspecialty or specialty, demonstrating solid performance with GPT 3.5 and then a leap forward in reasoning with GPT-4. And this was very exciting for the potential of these models. But as a brief sidebar, as you all likely are well aware of, it is important to note that multiple choice performance does not equal safe or effective care. So it doesn't really speak to direct clinical utility of these models. But these are still useful benchmarks for early exploration. So to be clear, it would be an error to judge LLM performance like humans, i.e. ChatGPT passing a multiple choice board exam does not mean that it has the capabilities of a physician in that specialty for many, many reasons. These models have limitations, but still, the early exploratory research showed a lot of promise. For instance, in this early JAMA Internal Medicine paper, ChatGPT answered questions from patients posted to an online forum on Reddit, and they found that ChatGPT's answers were more empathetic and overall preferred to responses from verified forum physicians. A key limitation, of course, is that the comparison group was forum responses rather than standard of care, but still very intriguing. So as mentioned, these models are far from perfect, so we need to balance the hype with reality. And speaking of hype, many of you have likely seen this meme. And although there's a lot of, I feel like there's a lot of hype. We need to balance it with the reality as well. But the reality, as mentioned, is that these models have a tendency to hallucinate, i.e. produce incorrect or irrelevant responses. So when ChatGPT was first released, you'll probably remember, if you asked it for specific articles, it would just make up fake references that don't exist. You probably remember that case, or the infamous case of a lawyer who used ChatGPT, cited a bunch of fake cases, and then was disbarred. Remember, think of LLMs as next word predictors that have a hazy memory of the internet's knowledge. So though hallucinations have been mitigated quite a bit in recent state-of-the-art models and with tools, they tend to hallucinate most in domain-specific areas like in medicine. And so as a result, many articles conclude that LLMs are not ready for clinical use. For instance, this Nature paper evaluated LLMs in clinical decision-making and highlighted some of these limitations, namely hallucinations and misinformation, which we talked about. LLMs also lack metacognition. Simply put, they produce overconfident and incorrect responses and don't understand their limits. Knowing your limits is one of the first things that we teach trainees in medicine. LLMs tend to struggle with complex reasoning. They can't do that much thinking per token prediction, and so can make simple mistakes when it comes to reasoning. They can perpetuate bias. They have sensitivity to inputs, i.e. obvious errors in the medical record can be propagated, amongst other limitations listed here. And I cover them in a bit more detail in my review here that's designed to be a primer for radiologists and other clinicians. So given all these limitations, you might think it sounds like LLMs are not really useful at all in medicine and in radiology. And it is true that these limitations do preclude us from just throwing these LLMs out of box into the deep end and relying on them as medical generalists. But this is where we make a key distinction. LLMs out of box are general purpose. They've been tuned for general use to be helpful, to be flexible, and to be creative. That's that post-training step. So we shouldn't really expect them to work that well for clinical decision-making. And important point, that does not mean that they cannot be leveraged to be incredibly useful in medicine today. LLMs can and must be intelligently optimized to be used in more narrow medical contexts. And this is going to help further mitigate or eliminate these commonly cited limitations to enable improved quality and efficiency in what we do. So what does that look like? So the main point here is that the inherent flexibility of LLMs means that they can be efficiently adapted and optimized to perform well on many narrow medical tasks. By narrowing the scope and optimizing the models, we can reduce hallucinations, misinformation, and bias. We can adjust parameters to make these models less stochastic and more predictable. We can use them securely via local deployment or secure cloud that is HIPAA compliant. And in narrow scopes, we can limit the impact of suboptimal data based on the application. One of the main points that I want to get across today before we dive into the clinical applications is how we can optimize these models to unlock powerful use cases in medicine, and that the flexibility of LLMs makes this process extremely user-friendly once you get acclimated. So we can't cover each in detail, but the classically described ways to optimize LLMs are one, prompt engineering, i.e. how we instruct the LLMs in natural language and what information we give an LLM for a task. This includes giving it certain amounts of knowledge in context and providing it with a limited number of examples of a task. Two, retrieval augmented generation, or RAG. This is the best way to introduce new knowledge to the LLM, or substantial subspecialty knowledge to the LLM. Essentially, you're connecting the LLM to your custom data. Basically, RAG is going to pull relevant custom knowledge into its context when it needs. So remember, LLMs, if we picture them as having a vague memory of the compressed internet data, it's going to be hazy with domain-specific knowledge often. So by putting knowledge in the context window, it's basically like refreshing its memory, and it's going to be much more accurate with that information. And three, fine-tuning, which involves giving the model many examples of input-output pairs that adjust the weights of the model itself, ultimately to better align with your intended use case. Fine-tuning is the best way to modify the behavior of the LLM to align with your narrow task. You can also easily adjust the parameters like I mentioned, like temperature, which control how random or creative the responses are. For instance, reducing the temperature is going to improve repeatability, which is often desirable in medicine. So if this is new, this can be a mouthful, but in reality, once you're acclimated, many of these are very user-friendly. In particular, prompt engineering specifically is a very easy way to explore the feasibility of certain use cases very quickly prior to any additional optimization if required. And prompting is often combined with these others to create useful applications. Okay, so how does all of this, how do these LLMs unlock clinical applications then? So I'm going to go through the radiology workflow from the time that imaging is ordered to after a report is issued to discuss how LLMs can improve care. And I'm going to highlight what we've done in radiology in both the research and clinical context. Again, to orient you to this chart here, on the outside in light blue here, we have each step in the radiology workflow as it exists today, including requesting the imaging, radiologist protocol in the imaging, interpreting the exam, issuing a report, and then that report being interpreted. And then on the inside in red here, we have potential automations of these tasks with LLMs, including automated clinical history, where we'll focus most of our time, auto protocoling, various reporting tools, and then custom transformations of reports downstream. There are actually a lot of commercial products available in many of these spaces that already promise improvements in efficiency and quality. But in general, research and validation tends to lag behind these claims. So some of the things that we've been working on, again, where we'll spend most of our time is on the article in question, so auto clinical history to get the information we need, auto protocoling, which we're working on implementing, various reporting tools like improving how we assign cancer risk scores and how we determine tumor resectability, and the things that we can do with that final report, like creating custom patient-friendly reports that meaningfully improve patient knowledge and experience. So again, we'll only have time to briefly touch on each apart from the clinical history, and I may have to skip some as well, depending on time. So let's dive right in, talking about this paper in more detail regarding the clinical history. So clinical history, as you know, is critical in imaging. But this is often what we get. Follow-up. What's the primary tumor? That impacts how we image and look at the images. Is the patient sick? Is there a specific question we should be answering? Or even this one, rule out a diagnosis. That's a real history that I've gotten more than once. Remember, the same imaging findings can mean different things in different clinical settings. Now, the fact that the clinical histories often lack key details is not new. This paper here at the bottom in JAMA is from 1963, titled "The Clinical History as a Factor in Interpretation." So this is really an age-old issue in radiology. A lot of work has been done to try to improve this. So there are many QI initiatives that have been attempted over the years to improve those histories, but it's really hard to change human behavior. And even the best QI initiatives in the literature have shown that they can make moderate improvements, but those improvements tend to decay over time, i.e., you remind people, they add the details for a while, but then over time they go back to including fewer or no details. So it feels like we're at a bit of an impasse. But what if AI could help bridge this gap and automatically improve the clinical histories that radiologists get? They could take extremely long clinical notes from the chart and in a matter of seconds, pull out the most relevant details for the radiologist who's reading the images. But unfortunately, we know and we talked about how LLMs are not perfect. They tend to hallucinate, they tend to make things up or get things wrong, and they can be dangerous. We mentioned how they can struggle with complex clinical tasks, and this is very specialized language in oncology, complex notes. So maybe this won't actually work, and maybe not so fast. So our radiologist here is clearly unhappy because he's worried that he's going to have to live with histories like rule out a diagnosis and go from there. And again, these things, how we protocol the study impacts how we protocol the study, whether we're going to see the tumor or not, and how we look at the images. There have been a lot of papers actually that show that the sensitivity for tumor detection is much higher when you have that clinical data. So the purpose of our study was to evaluate LLMs for generating clinical histories from oncologic imaging, or for oncologic imaging from clinical notes, sorry, and then compare them to the original histories that we got for completeness, quality, and radiologist preference. So to do this, we collected over 11,000 CT chest, abdomen, and pelvis performed at our cancer center from January to November 2023 and randomly selected patients for inclusion. We did this randomly rather than consecutively because booking times are often clustered by malignancy type, and we wanted to make sure we had a representative sample. We used 7 patients to inform training of the model, aka prompting of the model, and how we should ask the various questions and kind of specify what we want. And then a final test set cohort ended up being 200 patients. Next, we defined 10 clinical history parameters of interest. And so this was informed by previous QI or quality improvement efforts at our institution by some of our QI leads, Anya Kilar, Christine Soong, Sam Saba, and a few others from our institution. Next, we surveyed 10 radiologists regarding the importance of each of these features for inclusion in a clinical history on a Likert scale from not at all important as a 1 all the way to critically important at a 5. And here at green in the top are all of the parameters that were considered to be very important to critically important. Primary oncologic diagnosis, of course. Acute or worsening symptoms, of course. History of a secondary cancer, obviously going to change how we look at the study and how we even protocol the study. Reason for imaging, of course, and prior relevant surgery was also considered to be very important. Obviously, that impacts the anatomy quite a bit. So we used GPT-4, at the time the most performant LLM, via Azure OpenAI service and using our institutional accounts via secure HIPAA compliant or PHIPAA compliant where we are cloud. And then we prompted GPT-4 to generate a structured report, or structured history, I should say, that included all the relevant details: primary oncologic diagnosis, other cancers, reason for imaging, tumor markers, specific question, etc. We gave only a few examples of the task in context to explain and show the model how we want the outputs to look. And then we prompted the model with each of the 200 clinical chart in turn. So here's an example. Manual entry, rule out recurrence or metastatic disease. That was the original requisition. And then again, LLMs plugged into the clinical notes. This is kind of a structured output that we could have expected. And this is one that was actually an output for a patient. Tells you at a glance, the primary tumor, ovarian in this case, tumor markers, reason for imaging, clinical status, i.e., are there any pain or other symptoms that are present, past surgeries, etc. Okay, and this is the information that we would use to protocol and interpret the study. So we had two reviewers and a third tiebreaker radiologist reviewer perform reviews of the clinical notes and of the histories. So to define reference standard, the clinical notes themselves were reviewed to define the presence or absence for all of those parameters. For instance, was the primary oncologic diagnosis mentioned in the clinical note? Was it mentioned in the history? And they were blinded to the others when they were reviewing those. And then we did the same with the original history and the LLM generated history. And that allowed us to assess the LLM performance for extracting these details from the notes, including recall, precision, and F1, which was outcome number one. How well did they perform? We could also use the information to calculate the completeness of each history, i.e. the proportion of the original histories that included those details and of the LLM generated histories. And third, we did a pairwise comparison between LLM generated and original histories performed by the 10 radiologists who compared them on several axes. Most importantly, which they preferred at the time of CT interpretation. Okay, and on to the results. So these are the cancers that were represented in our cohort. So it was a pretty wide and diverse array of cancers, primary oncologic diagnoses in our cohort of 200 patients. And first, how did the LLMs do? So overall, you can see that they did very well with an overall F1 extraction score of 0.983. Okay, and you can see the performance for each of the parameters here that we don't have time to dive into in detail, but overall they perform very, very well. Okay, there were some hallucinations, namely for reason for imaging, for instance, it often inferred based on context the most likely reason for imaging, even when it wasn't explicitly stated in the note, hence the precision being a little bit lower there. And that could have been related to how we prompted it and how we asked it to classify that information. And with that knowledge, we would be able to adjust that for the future. With respect to completeness, again, these are the proportion of histories that included each of the items. So in green in this chart are the LLM generated histories, and in blue are the original histories. And so for the very to critically important items, the LLM generated histories were markedly more complete than the original histories. So for primary oncologic diagnosis, nearly 100 to 89%. For the presence of acute symptoms, about 15% of them had that noted in their clinical note, and the LLM picked up on almost all of them, versus only 4% of the original histories mentioned the presence of acute symptoms. The original histories never mentioned a secondary cancer in any of the 200, whereas 11% of them were found to have a secondary cancer based on their clinical notes, and the LLM successfully extracted that. And then you can see for the others, including prior surgery, 61% in the LLM generated histories versus only 12 in the original clinical histories. All of these were extremely statistically and clinically significant. At pairwise comparison by the radiologists much preferred the LLM generated histories for imaging interpretation. That's this line here in green versus the original histories in blue. So to reiterate, LLM generated histories were markedly more complete than current standard of care and were much preferred by radiologists over current standard of care. So we are working to bring this to practice, and I think we can talk about some of the risks, limitations, etc. But to me, looking at these results, which demonstrate very strong improvements over current standard of care, it feels wrong not to implement something like this as soon as we can, in supervised settings especially. Limitations, there were, of course, limitations to our study. Most importantly, it was a proof of concept study using retrospective data. And of course, implementation would involve additional complexity, but would be very doable. Okay, John, how are we doing for time? I just want to see um, how much time I should spend on each of these other things. I might just briefly touch on them, but
I think another 5 minutes might be good, and
sure.
then we'll leave some question time. Thanks.
Sure. So I'll just kind of do a cursory overview of the rest of them and not go into them in detail. But after requisitions placed, we need to protocol that study, i.e., determine how they're going to be done, and that's very important, crucial. It's also very time consuming for radiologists. It's been tried to be automated before with more traditional methods, but in general, we're trying to replicate in those situations how humans do it today. Whereas with LLMs, given the flexibility, it's a great fit. We can apply them to different hospitals' protocol lists. We can edit them at any time if there are new protocols or new ways that we want to, limit oral contrast or kind of policies change. And the LLMs may follow those institutional guidelines more faithfully than a big heterogeneous group of residents, fellows, and staff. So I won't go through the methodology, but essentially we used very extensive prompt engineering. The prompt is about 4 or 5 pages for CT abdomen and pelvis requests. And we also then fine-tuned a second model on, we had the prompt and then we also fine-tuned it on several labeled examples to see if that would improve it more significantly. And then we compared it to the human assigned protocols in practice. And we had blinded reviewers who didn't know if they were LLM history protocols or human protocols, and they categorized them as exact matches, equal alternatives, reasonable but inferior, or inappropriate. And in short, LLM generated histories much more frequently matched reference standard than the human assigned protocols and much less frequently assigned suboptimal protocols. So we're trying to bring this to practice now, but showing you an example of an LLM generated protocols that can improve how we assign protocols and also make us much more efficient. We also have worked on several reporting tools, and that includes categorizing pancreatic tumors with respect to the NCCN criteria automatically. So this paper is also in radiology if you want to look at it in more detail. But the idea is that this is a very complex clinical task, and out of box, LLMs will not usually perform very well. So we tried different prompting strategies, including giving it knowledge and context, and we talked about why that can be helpful, as well as something called chain of thought reasoning, where we said LLMs are generally not good at complex problem solving like this. And you can't cram too much reasoning into a single token prediction. So you have to spread that thinking and reasoning out. And so that's what chain of thought does. It generally helps with complex reasoning. We actually had it subclassify each vessel first and then use all of that information to then make the overall tumor categorization using NCCN criteria. And you can see that out of box in green here. So these are GPT-4 in green. This is accuracy categorizing tumors using NCCN. Out of box performed pretty poorly at 67%. In context knowledge significantly improved to 83%. And using chain of thought, accuracy of categorizing tumors by NCCN criteria was 92%, so quite high. It made our surgeons more efficient when actually consuming these reports and also made them more accurate when they themselves were triaging cases by resectability. And then lastly, we've been using it for some patient-friendly reports. There are some startups in this space that generally are trying to define kind of terms and do it from a different angle. But LLMs are a great fit for this because they can write things in appropriate grade level English and tailored to the patient. But they haven't really been widely adopted yet because there's, of course, some concern about heterogeneous language in reports and potentially giving incorrect information. And so we've been coming at this from a different angle, from a more narrow and limited angle. So we actually have a urologist who has already been working on patient-friendly reports in a structured format like this, where they actually manually took prostate MRI reports and then created these patient-friendly reports. They worked on the terminology, made sure they were patient-friendly, and found that patients improved understanding using those reports, found them more useful, had better knowledge and knew what to expect, and at the end of the day were less anxious and had more productive conversations. This was published on a few times. The problem with this, though, is it's not scalable. So we actually generated and created a tool that takes prostate MRI reports and will automatically, within the matter of seconds, generate the patient-friendly report, including drawing lesions in the right location in the prostate based on where they're described. And so this is only possible because now we have LLMs that can take unstructured text and complex reports and do many, many very quick and very accurate classifications on a per lesion basis to then be able to generate this accurately. So we're currently validating this, but we want to roll this out to make it more widely available. So in general, whether you're a researcher or looking for uses of LLMs and want to apply them yourself, I think it's important to look at kind of what clinical problems you see on a day-to-day basis, kind of see where those gaps of care are. And then if you know how LLMs work based on kind of what we described and your other knowledge, try to find things that live at the intersection between the two. And I think that when you use LLMs out of box and just throw LLMs at a problem, that intersection is actually pretty narrow. But even with just a bit of optimization and understanding again how they work, that overlap can grow significantly, in my mind, growing to many of the things or a substantial proportion of repetitive tasks that require language and thinking. Again, thinking or language is the code of thought. I did talk about kind of what comes next, but I'll briefly kind of just roll through this quickly. Multimodality. I talked a lot about text-based applications because that's my primary area of research and primary area of interest. But multimodal models are also, getting better and better by the day. I actually, medicine's inherently multimodal, right? The clinical data and text, medical images, pathology images. At the end of the day, medicine's all about reasoning over multimodal data. It can enable a very low latency conversational agents. So, for instance, if you've talked to the newest versions of these LLMs, the conversations have become very natural. So that could obviously, if optimized, be applied very nicely in healthcare. It also opens up new avenues to interact with the LLMs. So, for instance, I shared my screen, pulled up a CT, and talked to Gemini and posted this video on X or Twitter, and it ended up going viral. And it actually did a decent job of kind of knowing the basic anatomy, and it was kind of a very cool interaction. Someone stole the video and then reposted it with Matthew McConaughey here and a little meme making fun of radiologists and taken out of context, but it was pretty funny. And then the reasoning models, I talked a lot about kind of, GPT-4, GPT-4o, where the goal is to predict the next token in the actual answer. Reasoning models have this kind of chain of thought that I introduced earlier embedded into the model for all problems. So I talked about why we use chain of thought to spread out the reasoning over several tokens. These new reasoning models do that out of box, and they kind of via reinforcement learning are taught to do that. So for instance, I asked a reasoning model, and I should say these reasoning models are things like OpenAI's O1 model, OpenAI's O3 Mini, for instance, and DeepSeek R1. Those are all examples of reasoning models that are the new frontier. So rather than just predict the answer, it first generates a lot of tokens of thinking. And OpenAI kind of hides what those actually are, and they give a little summary before it provides the answer. But DeepSeek's R1 is open weight, and so you can actually see the raw thinking tokens here. So I gave the same problem to DeepSeek R1, and you can see that it just generates these tokens. Okay, let me try to figure this out. I remember the NCCN guidelines categorize tumors as resectable, borderline resectable, unresectable, etc. So it's kind of a very cool new frontier that's improving the way these models reason. And it'll be fascinating to see how we can harness this in medicine because medicine is inherently a high reasoning specialty or job. So that's what I wanted to cover. And so appreciate you having me here today. Again, the three main points. First, most importantly, I think optimizing existing foundation models already enables many clinical applications that can improve patient care. We showed some examples of that, but the possibilities, I think, are endless. I think we need to more aggressively collaborate between clinical and technical people with expertise. And while safety is, of course, very important, we shouldn't use that as an excuse to sit on our hands where there are clear benefits. We need to take the opportunity to implement these tools in practice in a safe, supervised way. So thanks a lot for having me. Appreciate it. And hopefully left enough time for some questions and discussion.
Perfect. Thank you so much, Dr. Bhayana. Um, we really appreciate you being here today and taking the time to share your work with us. If you have a question, just raise your hand.